All right, we're going to do a problem where we have a varying density. So if we put on an x and y axis a very thin rod so that we're going to assume that it's only one direction, but the mass distribution is not constant. All right, so just showing that there's less mass, then it goes into more mass. And we'll say that the function for lambda is some constant times x. So as x value increases, the density increases. Since it is a solid rigid object, we have to look at it in integral form. And what we know about linear density is it is the mass divided by the length. And for this problem, any small little packet of mass over any small change in that length. All right. So we don't know the mass, but we do know the density. So we have to start substituting things out to get rid of that mass, or we have to find out what that mass is. It looks like we can figure out what the mass is, so that if I rearrange this so that dm is equal to lambda dx, and we take the integral of both sides, if I add up all the little pieces of mass here, I will get a total mass. So the total mass is going to be the integral of lambda dx. But we know that lambda is a function of x. So let's substitute in kx for lambda dx. So the mass, and this is from 0, and we'll call this a length L, okay? This is going from 0 to L as our limit. So we're going to go infinite sum of the mass between this point on x and that point on x. So when we take the integral here, and what these limits mean is, first let's just change the function. So we take the integral function by adding 1 and dividing by it, and then that is going to be evaluated between two limits. Basically it's the final minus the initial. So you plug in the value for the variable, and you plug it minus the value of this variable. So that whole thing is 0, so that the total mass is 1/2 kL squared. So now that we know the total mass, we can actually make that substitution so that the xcm is equal to, if it's 1/2, that's going to be 2 over kL squared. And that's outside of the integral. And we have x, but we don't know the little mass, but we know that that little piece of mass value depends on the density at that location. So this little piece of mass depends on the density at this location. So we're going to use this same equation here and substitute it in for dm. So instead of dm, I'm going to put in lambda dx. So we also have to plug in the function for lambda, do one more multiplication here. So we have this function that we have to take the integral of with respect to x. So here it's x to the third, constant stays there, divided by 1/3, and now this is going to be evaluated between 0 and L times these constants. So of course when you put the 0 in, it goes away, so we're left with 1/3 KL cubed times 2 KL squared. These two L's cancel out two of those, this K gets canceled out, so we're left with 2/3L, and that would be the location of the center of mass of this rod, since more of the mass is distributed towards this end. So it'd be right there.